Hey, let's talk about binary representation of data. So, anytime we have any piece of information stored on a computer, it's stored in binary. Binary is a really simple system for encoding information. We use systems to encode information all the time. For example, this symbol set is communicating the information 17. This says cat. We use symbols to represent information all the time, and computers are no different. The only difference is that they use a really simple set of symbols. Now, we are often working with numbers, so let's just worry about numbers for now. And we use what's called a base 10 number system. Base 10, meaning that there are 10 symbols that we can use. Those symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Think about it. After that last symbol, we just start repeating again. So if I wanted to write the number 10, I would write 1, 0. Now, binary is a little bit different. It's what's called a base 2 number system. Base 2. Meaning it only has two symbols like we used, 0 and 1. Now you'll notice this number 10 uses a 0 and a 1, and that's in both sets. So this means two different things. It means one piece of information in base 10 and a different piece of information in base 2. So we're going to explain how base systems work to make sense of this particular number. So let's start with base 10. We have a number, let's call it 458. And the reason I said 458 is because there's a 4 in the hundreds column, and there's a 5 in the tens column, and an 8 in the ones column. So 458. The way I got that is 4 times 100 plus 5 times 10 plus 8 times 1, which of course gets me back to that number I started with. We don't realize it, but when we're working in base 10, we're doing this math all the time. It just so happens that we're working with a really simple number system based on the 10 digits we have that make it easy to combine and recombine these numbers. So what does it look like at base 2? Well, suppose I have just two numbers, like 1 and 0. Well, this spot is the 1 spot, but that's not the 10 spot. That doesn't really make much sense. Because if I skipped right from 1s to 10s, how would I represent the number 7? Now, the base here is 10 because this column is 10 to the 0. This column is 10 to the 1 or 10. This column is 10 to the 2 or 100. So we use the base 10 over here. Let's use the base 2 over here. 2 to the 0 is equal to 1. But 2 to the 1 is not 10. 2 to the 1 is 2. If we added a third piece to it, we'd have 2 to the 2, or a 4's column. So if I were to write this number, 110 in binary, it would mean I have 1 4, 1 times 4, this is the 4's column, the 2's column, 1's column, plus 1 times 2, plus 0 times 1. 4 plus 2 plus 0 equals 6. That's the number 6 in binary. So we're using the exact same system to represent information, just working with a different base. Now, going back to our original number. In base 10, this is obviously the number 10, but in base 2, it would be 0 1s and 1 2, so this is actually the number 2. Now, there's one more system that's pretty common in computing systems, and that's hexadecimal, or base 16. And in that system, we have 16 symbols. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then once we use up all those numeric symbols, we go to A, B, C, D, E, and F. A really common place for using this system, which is called hexadecimal. Hexadecimal is when you're storing colors on, say, a web page. So colors are always made up of a red, a green, and a blue value. And rather than have a long string of numbers to say which color you want, we use hexadecimal digits. So what we might say is I want the color turquoise, and maybe that's 1B6FA2. And that's just a number, just like this is a number and this is a number, just written in a slightly different language or number system. So again, we have base 16, which is hexadecimal, base 2, which we call binary, and then base 10, that's what we work with all the time, that's called decimal. So there's a quick breakdown of how we store information on computers, how binary works, and how to go from binary to decimal to hexadecimal and back again. Bye now.